For this lesson and for the start of our new unit, we're going to be looking at quadratic relations. And we're going to start off by comparing what we know about linear relations to what we can start by observing in our quadratic relations. So if we take a look at a linear relation, y equals mx plus b, that's the standard equation of a straight line. And so some of these values that you should already be familiar with, we've got the value for m, and that's the slope of the line, and we have b, and that's the y-intercept of the line. So that's the first thing of significance in the equations. The second thing you might notice is that for the quadratic relation, we also have, so we've got variables. We've got our x, which is our independent variable. We've got our y, which is our dependent variable. With the quadratic relation, we also have an x. Here's x appearing twice. That's a little odd. We've got y. And then we have these values a, b, and c. And in mathematics, we typically use x, y, and z for things like variables, and we'll use a, b, and c or other letters to represent not necessarily constants. They could be constants or they could just have other significance. In this case, we've got the slope and the y-intercept. These a, b, and c, they also have meaning that we're going to explore a little bit later. So the first thing to point out here is we've got these familiar ideas, the slope, y-intercept. For now, we're just going to call these coefficients. Coefficients are the numbers, or in this case, they're variables that will be replaced with numbers that go in front of our independent or dependent variables. So a, b, and c are coefficients. The other thing you might notice here has to do with the form of the equations. Not only does this equation have an extra term in it, but here we have mx to the power, and although we don't write it, that's to the power 1. And this one is actually, we never write it this way. I just want to illustrate something here. This one is bx to the power 0. Now, if that doesn't seem familiar, if you're not comfortable with that, I don't want you to worry about that too much. I just want to point out to you that here we have an exponent of 1, and in this case we have an exponent of 0. On the other hand, here we have ax to the power 2. So here our independent variable is squared. And then we've got a bx to the power 1. And similarly over here with the c, this is cx to the power of 0. So here we have to the power 2, to the power 1, and to the power cx to the power 0. So the significance of that is that that is something called the order. When we talk about the order of an expression or the order of an equation, we're talking about the highest exponent of the independent variable. Now we do have to look at the dependent variable. I don't want to get into too much subtlety about that right now. So for the time being, we're just going to look at the independent variables, and we're going to be looking at the highest number that goes with the exponent of the independent variables. In this case, the highest exponent is 1, and in this case we have the highest exponent of 2. So this is an order. So this is an order 1 equation, and this is an order 2 equation. An order 1 equation is linear, an order 2 is quadratic. And I believe I've just got that summarized on the next page, just a little cleaner. Okay, so now, when we're introduced to a new relationship, our first plan of attack is almost always to create a table of values and graph, so we can get an idea of what this thing is going to look like. You pick some values for x, and I didn't say this, but in general, we want to center those values around 0. That's not always going to be the case, and we're going to have an example here in this lesson where that's not necessarily the case, but that's usually a good idea. If you don't have an idea to start anywhere else, start with an x value of 0 and then go on either side of that x value. So go 0 and then +1, -1, and then maybe go to +2, -2, and then get an idea of what your graph is going to start to look like, whether or not you need to shift this kind of center point. But we usually want our center point to start at 0 if we don't have any other information. We're going to substitute each x value into the equation. You should be familiar with that idea, substitution. Determine the values for y after you make that substitution, and then we'll plot the points. We're also going to be looking at in this lesson, so if you don't remember first differences, I'm going to remind you of how to calculate first differences. So that's the differences, which means subtraction between consecutive y values for consecutive x values. This is something that's not emphasized enough, and it's not even emphasized enough by me, even though I'm mentioning it here. So I will be pointing this out periodically as we go through not just this lesson, but through these concepts dealing with first differences. Okay, so here is a linear. This is a linear equation, y equals 2x plus 1. It is an order of 1, and so it's linear, and we're going to get a straight line from this. So this should all be review material from grade 9 or even earlier. So I'm going to start with a table of values. You could create, like I said, when we've done linear values in the past, quite often you've created your table of values like this. Now that we're moving to quadratics, just in general, good idea is to start your table of values centered on 0. Not only is this generally a good idea for quadratics, but it also might get you some extra practice substituting in those negative values, trying not to make a mistake there. So y equals 2x plus 1, so that's going to be 2 times bracket. Instead of the x, we put a negative 2 plus 1. That's negative 4 plus 1 is negative 3. And then we end up with 2 times negative 1 plus 1 is negative 2 plus 1 is negative 1. 2 times 0 plus 1. 2 times 0 is 0 plus 1 is positive 1. 2 times 1 plus 1 is equal to 3. And 2 times 2 plus 1 is equal to 5. Now let's take a look at those first differences. The first differences are always the second y value minus the first y value. So when I do my first differences between here and here, it's always the second one minus the first one. And so it's going to be the number negative 1 minus the number negative 3. And you can see this becomes negative 1 plus 3 because we've got a double negative here, and so that's simply equal to 2. And then when I do this next one, it's going to be 1 minus negative 1. And that double negative, that becomes 1 plus 1, that's equal to 2. 3 minus 1 is equal to 2. 5 minus 3 is equal to 2. And as you can see, and I've got this down at the bottom, in a linear relationship, what can we say about the first differences? And in this case, you can see the first differences are all the same, or constant, I believe is what I was. Okay, moving on. Taking a look now at a quadratic, the most basic quadratic relationship you can come up with, y equals x squared. This is also referred to as the parent function for all quadratic relationships. They all start with this. So again, start with that. And now it's going to be x squared, which is negative 2 all squared. It's negative 2 in brackets. And this is very important because negative 2 times negative 2 is actually equal to positive 4. And it's really important that you get that result here. If the negative sign is outside of the brackets, it will be a negative. If the negative sign is inside the brackets, it's going to be squared. That's going to turn into a positive. So negative 1 all squared is equal to positive 1. 0 all squared, 0 times 0 is simply equal to 0. 1 squared is equal to 1. 2 squared is equal to 4. So an interesting result here. Even though my x value was negative, when I squared it, I got a positive. My positive value, when I squared it, I got a positive. So this is definitely not a linear relation. So let's see what can we say about this. So let's do our first differences. So it's going to be the second one minus the first one. So that's going to be 1 minus 4. That gives me negative 3. The second one minus the first one, that's 0 minus 1. That gives me negative 1. 1 minus 0, that gives me 1. 4 minus 1 is equal to 3. So the first thing we notice here is that these first differences are not the same. So they're not the same. They were the same for a linear relation. This is obviously not a linear relation. We knew that already from the equation. This is just another way of determining that. So let's take the next step. Let's do the second differences. Now we get negative 1 minus negative 3. Again, there's that double negative. We have to be careful about this. So that becomes negative 1 plus 3. And so that's going to be equal to positive 2. We end up with 1 minus negative 1. Double negative becomes plus 1 plus 1 is 2. And we have 3 minus 1. And that is simply equal to 2. Now take a look a little bit at notation here. So here is my independent variable. Here is my dependent variable, which is defined in terms of my independent variable. So y equals x squared. Delta y means the difference in y or the change in y. So how are these y values changing? And that's known as the first differences. Now, one of the things that first differences does assume is that your delta x's are all constant as well. And there's not a lot of room here, but just off to the side here, negative 1 minus negative 2 is the same as negative 1 plus 2. That's equal to 1. 0 minus negative 1, that's 1. 1 minus 0 is 1. 2 minus 1 is 1. In order for any of this work dealing with first differences, second differences, for any of it to matter, for any of it to be legitimate, your differences in your x's, your delta x's, must be constant. And that's something that I don't think is said enough, not even by me. So going back, we've got delta y, those are known as the first differences. You can see delta x, those are the first differences in x. And so we use this short form notation for second differences. Delta squared y represents the second difference in y. So take a look at our quadratic relationship here. What can we say about our first differences? Our first differences are actually different, whereas our second differences are constant. So that is a test for a quadratic relation. First of all, if the first differences are different, you've eliminated linear. And if the second differences turn out to be constant, then now you know it's quadratic. If your first differences are all constant, you don't go any further, because once you've shown that it's linear, there's no point in going further from there. It's always what differences are the first ones to all be the same. And later on, as you go on to further math concepts and different courses, you'll find that sometimes, even then, first differences, second differences, third differences, they never end up being the same, and that's a different kind of mathematical relation. Okay, we were asked to create a table of values, but we were also asked to graph this. So let's go ahead and graph this. I'm going to set my scale a little bit wider because I know I've got the room for it. So I'll set that as 1, 2, 3, -1, -2, and -3. 1, 2, 3, 4, 5. And I know I don't need to go into the negative here for y. There's no negative y values. So at -2, I have a value of positive 4. At -1, I have a value of positive 1. At 0, I have a value of 0. At 1, I have a value of positive 1. And at 2, I have a value of positive 4. So these are my x values. So I'm reading along my x-axis, my y values. And then you take a look and you try to draw. Now it's not a straight line. Don't get your ruler out for this. I don't want to see a game of connect the dots on these points. That is absolutely wrong, because if we were to do our table of values for the points in between here, they wouldn't be straight lines. So what you need to do, and it can be difficult, is you want to draw just a nice smooth curve, as smooth as you can manage, that goes through these points, and then an arrow to show that it keeps going. Down here at the bottom, it's supposed to be like the letter U, so don't make it come down to a V. Smooth curve through there. It's not going to be perfect. We accept that. That's okay. But just try to make sure you've got a nice smooth curve at the bottom here, and then do your best to go through those points. And this is a new shape. This is actually called a parabola. And we're going to be seeing a lot. I could at least spell it nicely and neatly if we're going to be seeing a lot of this, which we are. Okay, so this is a parabola. This is the graph y equals x squared. Okay, another table of values for the graph y equals negative x squared plus 2x plus 3. So it looks quite a bit more complicated. We've got that negative in front, and I'm going to stress that right up front. That negative is in front. So you'll notice when I put my values into my equation, when I substitute here, pay particular attention to how that negative comes into play. And you can see I've also shifted my table of values here. Now I had the benefit of knowing what this graph is going to look like based on experience. But for you, again, start centered at 0 and then see whether or not you have to build points in either direction. So in this case, I'm telling you to do your points here. So we get negative, that negative sign, and then I replace the x. So I'm going to be particularly careful for these first couple of examples. So instead of x, I put a negative 1. Then I square that bracket. Order of operations is going to be very important here. 2 times x, which is negative 1, plus 3. Now this might be a lot to do in this space. I'm going to squeeze the answer in here, but I'm just going to come down to the bottom here and say, okay, so I've got negative times negative 1 all squared plus 2 times negative 1 plus 3. So that negative sign in front stays because the first thing I do by order of operations is that. Well, what is negative 1 all squared? That is positive 1. And then I've got 2 times negative 1, that's minus 2. And then I've got plus 3. Negative of bracket 1 is that's just the same as negative 1 minus 2 plus 3. That's negative 3 plus 3 is equal to 0. So take a look at that. Make sure that that's not something that's going to trip you up. Some students are going to get tripped up by this. You just need to practice it enough, make enough corrections that it doesn't affect you anymore. Negative, in this case I'm substituting a 0. That's an easy substitution. Plus 2 times 0 plus 3. So I'm going to do this one without writing it out. This is 0, this is 0, plus 3 is simply equal to 3. Negative 1 squared plus 2 times 1 plus 3 equals, so this 1 squared is 1, so that's negative 1. 2 times 1 is 2, so this is negative 1 plus 2 plus 3, that's equal to 4. And then we have negative times 2 squared plus 2 times 2 plus 3 equals 2 squared is 4, and that becomes negative 4. 2 times 2 is positive 4, so negative 4 and positive 4 is 0, giving me 3. 3 squared plus 2 times 3 plus 3 equals 3 squared is 9, so that's negative 9. 2 times 3 is 6, so I've got negative 9 plus 6 is negative 3. Negative 3 plus 3 is equal to 0. So there are my y values, 0, 3, 4, 3, 0. My delta y's, first differences, my delta x's, you can see they are already delta x's of 1. They're all consecutive. So my delta y's, my first differences, 3 minus 0 is equal to 3. 4 minus 3 is equal to 1. 3 minus 4 is negative 1. 0 minus 3 is negative 3. First differences are not the same, therefore it is not linear. That doesn't mean it's quadratic, it just means it's not linear. 1 minus 3 is equal to negative 2. Negative 1 minus 1 is equal to negative 2. Negative 3 minus negative 1 equals, this becomes positive. Negative 3 plus 1 is negative 2. My second differences are all constant. It's a quadratic relation. Also, this time I got second differences were negative as opposed to positive. So what impact might that have on the overall quadratic relation? So once again, I think I can space things out a little bit. Always try to make good use of your grid space, so you don't feel locked into always doing 1 square is 1 unit. In this case, I'm doing 2 squares as 1 unit because that allows me to spread out my graph. I'm not trying to squeeze my graph into a tiny space. The larger your graph is in general, the better that's going to be for you to be able to see features of the graph. Okay, so when x is equal to negative 1, y is equal to 0. When x is equal to negative 1, y is equal to 0. Maybe I'll switch colors for that. Could have done that on the previous one as well. So there's a point. When x is equal to 0, y is equal to 3. When x is equal to 1, y is equal to 4. When x is equal to 1, y is equal to 4. When x is equal to 2, y is equal to 3. When x is equal to 3, y is equal to 0. So now we have that same, again, we're not going to connect the dots on this, we're going to try to draw a smooth curve. Sometimes one of the things I recommend is actually draw that smooth curve at the base first, and then fill things in as you can. Another error that occurs, you can see even there, especially this tablet, makes it a little awkward to do this all in one shot. But watch out, another thing to watch out for is that it never goes vertical, and it certainly never curves back on itself. One of the mistakes that I see people making when they draw parabolas is they end up looping it back, something like that. That's really exaggerated, but I've actually seen probably that bad before. So just try to make sure, see there, even there I was making a mistake. It's got to be curving, but not, it doesn't get vertical. It's always getting steeper and steeper. And you have to understand there's always going to be some room to make mistakes here. The way you avoid that is actually the more points you put on here, the better it will be. Okay, so there is the quadratic relation y equals negative x squared plus 2x plus 3. Notice that I really emphasize that negative sign for when we were creating our table of values, but also notice that this parabola is curved the opposite way, and that's related to that negative sign as well. So when we've got a parabola in this form, ax squared plus bx plus c, the direction of opening, and that's what I was just talking about. Well, you can read that from the graph. The direction of opening is where is the open side. In this case, the open side is pointing down, whereas if we go back, in this case, the open side is pointing up. So if we have a positive a value, if the value in front of x squared is positive, that will result in a positive second difference. That's another way we can look at it. And in those cases, the parabola opens up. If we have a negative a value, just like the previous example we did, that resulted in a negative second difference. And as you can see from the graph, the parabola opens down. And that's it for this lesson.